Before we come to our special cases of the broadcast channel, we want to look at some basic properties. The first property is more or less simple. So that is, we can use a common message as dedicated message. That means if I have this triple R0, R1, R2, then also alpha 0, R0, R1 plus alpha 1, R0, R2 plus alpha 2, R0 are achievable. What does it mean? So somehow one really used the common messages for the dedicated messages. Let's look at the most simple case. Let's assume the common message set is M0. It goes from 1 to 2 to the n R0. And the message set, the dedicated message set for the first decoder is M1 and goes from 1 to 2 to the n R1. And each message corresponds to a number. Now let us assume for some reason no common messages is needed at all. And we allow the first decoder to use all bits, all information of the common message. So what he can do then, we can map the product of M0 and M1 to a new message set. So this is then the message set, of course, as written there. And it's like in binning. So then here, of course, for M1 let's call this M1 head. If I can now have no common messages and M1 can use all these common messages, then we call it M1 head. And this M1 head, of course, it's like in the following. Then here you have for M1 the message 1, 2, 3, 4, 5. And here now you have the message 1, 1, 1, 2, 1, 3, until 1, and then we have 2 to the n R1. And then the next message comes, 2 to the 1 is one message until we reach 2 to the 2n R1, and so on. That means in totally we have, in this case, we can use the whole sets. So if we have here 0, so we know then if we can achieve R0, R1, and R2, what I just showed you, then we can also achieve 0, R1 plus R0 and R2. And of course, the same is possible for R2. And then, of course, you just can use half of the messages, or you can use alpha 1 of the messages and alpha 2 of the common messages for R1 and R2 to generalize this. And then the third thing, what is this alpha 0 for, is just that you cannot use not all common messages. That means you reduce just the number of common messages, and then you get this formula. And so we know if we can achieve this, if we can achieve R0, R1, R2, then we can also achieve alpha 0 times R0, R1 plus alpha 1 R0, R2 plus alpha 2 R0. Of course, all alpha e's must be bigger equal 0, and all the alphas have to sum up to 1. The second property is it's perhaps a little bit surprising, but not so difficult to prove. So if you look at a broadcast channel, then the theorem told us that the broadcast channel only depends on its marginals. That means if you have a general broadcast channel, PY1, Y2, depending on X, then it just depends on PYX, PY1 depending on X, and PY2 depending on X, which are the marginals of this channel. And the theorem says if I have another channel, let's look at this tilde channel, PY1 tilde and PY2 tilde, and depending on x, so it's a channel from x to y1 tilde and y2 tilde, such that the marginals are the same for all a and b, then the channels are also the same. That's very, at first moment it's perhaps surprising, but let's look at the proof. So we look at the error event E1. The error event E1 is just an error of the decoder 1. That means the estimate of the common message and the estimate of the dedicated message is not equal to the common message and the dedicated message for him. It's the same, in the same way we define the event E2. So we have the errors PE1, which is the probability of the event 1, and the PE2, which is the probability of the event 2. And then we can look at the error, which is just the union of event 1 and 2. And we know if we take the maximum over these two errors, PE1 and PE2, of course, this maximum is smaller than PE. But the sum of these two may be bigger than PE, because perhaps the errors are, the events are not disjoint, which is mostly the case. Then we have this inequality. We have the maximum of PE1, PE2 is lesser equal than PE, is lesser equal than PE1 plus PE2. That's not so difficult to see. But now if you look at this inequality, we see PE is small if and only if PE1 and PE2 are small. But PE1 and PE2 only depend on the marginal channels from x to y1 and from x to y2. So the same holds for any other channel. So that means that if we have a channel with the same error probabilities, then we get the chain broadcast channel. So if the marginals are the same, then we get the same broadcast channel. And that's the proof of the theorem. And of course of this theorem, it's we can restrict our attention to broadcast channels where we have a Markov chain, y1, x, and y2. But you will see in our proof that sometimes we don't restrict, do not do this restriction, because it's sometimes useful to have some dependencies.